Hello everyone, welcome to lecture on solid state. There are some properties of a solid state, namely they have definite mass, volume, shape, intermolecular distances are short, intermolecular forces are strong, compressible, rigid, so on. These are all we know. Let me quickly go through that. Solids can be classified as crystalline or amorphous. What is the difference between crystalline and what is amorphous? In this chapter, we may not be studying about amorphous. We will be concentrating only on crystalline substances. But we definitely do talk about differences between a crystalline compound and a amorphous compound. So, crystalline solid has long range order. What is this long range order? A regular and a repeating pattern like this. You can see that these constant particles, this can be an atom, this can be a group of atom, which we call it a compound, or it can be an ion, right? So this we call it some particle, which is a this is regularly repeated in a 3D geometry. This gives us a lattice. So this is a crystal lattice. Yeah, it has a regular repeating 3D arrangement of particles. The particles, when I said, again I repeat, it may be an atom, it may be a compound, it may be a molecule, it may be an ion. Okay, so let's look at one smallest section of that particular crystal lattice, which upon repetition over the 3 dimensions will give you lattice. So this is called a unit cell. Unit cell is which on repeating in all the 3 dimensions gives you a lattice. So this is a unit cell. Okay, let's talk about this unit cell. Dimensions along the 3 edges are A, B and C. It has angles alpha, beta and gamma. Alpha is the angle between side B and dimension C. So that is alpha, and the other angles are beta and gamma. So this is about a unit cell. What is a unit cell? Unit cell is a smallest group of atoms which represents whole of the lattice, whole of the crystal. This unit cell upon repetition all over the 3 dimensions produce a lattice. This is the smallest structure which we understand and analyze whole of the crystal. So there are total 7 crystal systems. I'll just go through them: cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, triclinic. I'll come back to all of them again, but let me first concentrate on this cubic system. 3 cubic lattices are there. They are primitive, body centered and face centered. Let's talk about this primitive cubic unit cell. This is one of the unit cell that we have in syllabus for IIT. Let's take a cube and let's try to put 8 atoms at 8 corners of this particular cube. So I have 4 here. Over this 4 I have 4 more atoms coming, and then okay, this is something like this. So this is called space filling structure. This is actually how they are arranged in the 3D structure. So there is something called effective number of atoms. If you look at this unit cell, though it is made up of 8 spheres, 8 atoms, not all of them are fully inside it. So if you come to the contribution side, this sphere, is only 1/8 inside the unit cell or a cube. So there are 8 corners with 8 atoms with 1/8 contribution from each side. So each unit cell owns one atom. So though you make one unit cell with 8 spheres, effectively you have only one atom in a sphere. So now it's about coordination number. What is coordination number? The number of atoms surrounding an atom. Let's take this atom. Let's find out all the number of atoms that are surrounding it, which are at an equidistance from this particular atom. So I have 3 atoms which are at a distance of a from this particular atom, and so is coordination number going to be 3? Let's see that. Let me extend these coordinates. I have 3 more which are at a distance of a. Though they are not, these 3 are not there in this particular unit cell, they belong to some other unit cell. Still, they are at a distance of a from this black atom. So coordination number is 6. So if a is the length of the cube, so cube has only one dimension, that is a. If a is the length of the cube, then a is equal to 2r. How do I get this? Look at this. This is the side. This is a, and here they are touching each other. These spheres are touching each other. So this is called open structure. In open structure, though we write centers of the spheres only. We don't write whole sphere because we want to see the geometry of this structure. So we write this open structure. This doesn't mean these two will not touch each other. Actually, this sphere which is at this corner, this sphere which is at this corner are touching each other. You can clearly see this here. If that is the case, then A is equal to 2r. So okay, let's talk about this density. Density is mass by volume. Density of this particular crystal is same as density of the unit cell. I mean, it's good enough if you can find the density of a particular unit cell, because that will be the same as the density of the crystal. So density is mass by volume. Mass is mass of each atom into n. Look at here, this mass means this is the mass of unit cell, and it has n is the effective number of atoms in a unit cell. It has n atoms, and that multiplied by mass of each atom gives you the mass of unit cell. And mass of each atom, how do we get it? Like we don't talk about mass of unit one particular atom. We talk about mass of 1 mole of atoms. So if you want mass of 1 atom, so you have to divide that with Avogadro number. So m is the gram atomic weight of the crystal, n is Avogadro number, and the density becomes n into m by v into n. So v is the volume. So n into m by n, this particular m by n gives you the mass of one particular atom, and the unit cell has, let's say, n atoms. Then this is mass of this total thing is mass of a unit cell divided by volume. You get it as mass of density. Okay, so for a primitive unit cell, density again is D is equal to nm by Vn. Volume is V cube. We know that volume of a cube is a cube. Here n is 1. Here n is 1 because we have just seen that there are 8 corners. 8 into 1 by 8. Effective number of atoms in a unit cell is 1. Okay, so now packing fraction. Let's see what is packing fraction. If you look at carefully, I am trying to fill a 3-dimensional space with spherical atoms. So I may not be able to fully fill the three-dimensional space. There are going to be some kind of voids. You can see some void here. There is some void here. So that means all of this space is not fully filled. So packing fraction is the fraction of total volume occupied by the atom. So if A cube is the volume of the cell, this whole of A cube is not filled. Some amount is going to be a void. So if I want to find out this packing efficiency or packing fraction, so I have to find out actual volume of the atoms by the volume of the total cell. So that is packing fraction is equal to 1 into that 1 is the number of atoms that are there in one unit cell, and you know that it's 1 per primitive cubic cell, and 1 into volume of unit one particular atom divided by volume of the cell. Where A is 2R, we just have seen it. This is the length of the cube, that is A, and that is equal to R plus again R. So A is equal to 2R. If I substitute that value here, I get it as 0.52, that is packing fraction. Along with packing fraction, we also define void fraction. This is again fraction of the void that is present in a particular unit cell. So that value eventually comes out to be 0.48. This is about packing fraction. Okay, I have a, now let's go to body centered cubic cell. Let's see what is a body centered cubic cell. Okay, this is again a cube. It has 8 corners. You have 8 spheres at the 8 corners and 1 at the center of the cube. So this what is the color, whatever, maybe some reddish color. This red colored spheres are at the corners of a face, and over it I have placed a sphere which will come in the center of the cube. So you have something like this. You have this one at the center. Of course you have 8 at the corners. I didn't represent here. Actual diagram, actual setup will be something like this. You can see there's going to be some 1, 2, 3, 4 here, 4 above, in between 1. So there are going to be 7 atoms that will make a particular body centered cubic unit cell. Let's come back to this effective number of atoms. You can clearly see that though this unit cell is made up of 7 spheres, 7 atoms, not all of them are fully inside this unit cell. Some part of some cells is inside some other unit cell. So if you look at this, you have 8 into 1 by 8, so 8 corners, 8 into 1 by 8, and 1 at the center, so 1 into 1. So that is effectively you have got 2 atoms. That means each unit cell owns 2 atoms. So effective number of atoms is 2 for this BCC. Coordination number, we discussed the coordination number for primitive cell. We decided it was 6 there. Then we tried to identify one particular atom there, and I counted all the atoms which are nearest to that particular one. So let's do something like this. Let's find out what is the coordination number in BCC. Okay, I'll take this particular sphere which is at the center of the cube. This is clearly is surrounded by 8 spheres which are at the corners of this particular cube. So you can see that yellow sphere which is inside is surrounded by 8 spheres. So coordination number is 8. The number of atoms surrounding an atom, that should be the coordination number. Okay, let's talk about this body diagonal. I have a cube, you have a body, you have a cube, you have a body diagonal. So if D is the length of the body diagonal, this is the body diagonal. If D is the length of the body diagonal, can you get a relation between this D and this length? A is the length of the cube. So before that, you can say that A is equal to R plus 2R plus R gives you 4R, right? So how do I get this? Like, you take this body diagonal from here to all the way here. In between you have R, again you have 2R, again you have R. So D is 4R, and also you know that D is equal to square root of 3A. From geometry you get this value by applying Pythagoras theorem maybe twice. Like, you get first you get this phase diagonal, then apply Pythagoras theorem with this phase diagonal and this side A, that you get it as root 3A as the body diagonal, length of the body diagonal. From this you can clearly write that 4R is equal to square root of 3 into A. That is a relation between A and we had a relation earlier. We had, when we were talking about a primitive cube, their relation was different. There you got A is equal to 2R. Now we have got 4R is equal to root 3A. Again, let's talk about the density. Density of the crystal is the same as density of the unit cell. So it's good enough if you find the density of a particular unit cell, and that should be the density of whole crystal. Again, density is mass by volume, mass of the unit cell by volume of the unit cell. Mass of the unit cell is equal to number of atoms in a unit cell multiplied with mass of each atom, and we know how to get the mass of each atom, that is gram atomic weight by Avogadro number. So if I substitute these values here, you'll have D is equal to Nm by V into N. What is this N? This is the effective number of atoms, that is number of atoms that are present in a particular unit cell. So that value is 2. We got it right. 8 into 1 by 8 plus 1 into 1, which was at the center of the unit cell. Okay, here we know that volume is A cube. So let's get back to this packing fraction for this body centered. We got packing fraction for a primitive cell. That value was around 0.52. That means only 52% was filled there. Let's see how much of it is filled here. Let's see whether it's more than 52% or less than 52. Again, packing fraction is a fraction of total volume occupied by the atoms. Okay, so packing fraction is 2 into volume of the atom by A cube. A cube is the volume of the cell, and there are effectively 2 atoms in this BCC. There are effectively 2 atoms in BCC. So, and each atom has a volume of 4 by 3 pi r cube. So total actual volume that is occupied is 2 times of 4 by 3 pi r cube, but volume that is present in a cube is A cube. So you got to have a fraction. Before that, you need to have a relation between A and R, which is derived. 4R is equal to root 3A. If you go along a body diagonal, you'll have R plus 2R plus R. That is equal to root 3A. So from that, if you do this arithmetic, you get 0.68. This is the packing fraction. That means only 65% is filled. Rest, that is 32%, is just vacant space which exists in all the BCC unit cells. Okay, so void fraction is 0.32. That is 1 minus packing fraction. Okay, face centered cubic cell. Again, this is a cubic cell, 8 atoms at 8 corners, and you have extra atoms at the centers of the faces also. Let's take one face. I am looking at one particular face here. These are the corners of the face, and I have one sphere at the center of the face. Okay, let me complete this unit cell. We have this looks something like this. There are going to be again 8 spheres at 8 corners, 8 atoms at 8 corners, and there are going to be 6 atoms at the centers of all the 6 faces. You can clearly see that here. 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 which are at 8 corners. Plus there are going to be 6 atoms which are at the centers of the each face. So 8 atoms at 8 corners of the cube, and you can see this. This is the blue spheres which are at six centers of the six faces of the cube. Now, this is actual scenario. I don't know whether you can make out something in this, but no, in actual crystal, you don't have these lines demarcated. See, these are our lines which we draw so that we'll understand what is the shape of this structure. In real life, we have something like this. If you properly observe, you have one face. You can see that 1, 2, 3, 4. This constitutes one face and one at the center. So same thing is happening everywhere. Again, you have adjacent face 1, 2, 3, 4, 4 atoms at the corners, one at the center. So how many atoms are there? 8 plus 6 will make a model. 8 plus 6, but that's not everything. Like let's look at this diagonal, phase diagonal. This time we'll look at phase diagonal because atoms are touching along a phase diagonal. Earlier in BCC, atoms, because one you have at the center, atoms are touching along the body diagonal. But in this case, atoms are touching along the phase diagonal. So I want to talk about this phase diagonal now. That is D, and you know that D is equal to R plus 2R plus R. This is R, this is 2R, this is again R. So D is equal to 4R, and you know that D is equal to square root of 2A. Hence we have 4R is square root of square root 2 into A. So that's the relation between A and R. So effective number of atoms. Let's see how many atoms in particular. We have just discussed that 8 plus 6 will make a model, but are all these 14 atoms are completely inside this unit cell? Definitely no. So let's see how much of it is inside, and look at here. There are 8 corners, again 8 into 1 by 8, plus there are going to be 6 spheres at the centers of each face. So 6 into 1 by 6. So there are going to be effectively 4 atoms that are present in a FCC. So let's see what is this, how far is this A and B are, like do A and B touch each other? That is the point. What is A and B? A and B are the atoms which are at the centers of the adjacent faces. Okay, we know that D is equal to 4R, that is root 2A. Just now we got it from phase diagonal. So that becomes 2R is equal, I divided both sides with 2. Okay, let me draw a line between A and B, and I got a triangle here, this point being the center of this particular edge. So I got a right angle triangle here, that is this one. So you have what is the length of this length? That is A by 2, this length A by 2. So this has to be A root 2 by 2. This length has to be A root 2 by 2. Why is this length A by 2? Why is this length A by 2? You can see that you are trying to measure the distance from the center of the cube to the center of the edge. That is half of this whole length. That is A by 2. So this is also A by 2. A by 2, A by 2 gives you A root 2 by 2. So you can clearly see that 2R is A root 2 by 2, and distance between A and B is also A root 2 by 2. So we learned in maths that condition that a sphere or a circle touch each other is the distance between the centers should be equal to the sum of their radius. So here the radius for both A and B is R. So distance between A and B is 2R here. Hence A and B touch each other. This is a point. I don't know. We should be able to notice that. We should be able to understand, appreciate that these spheres at centers of the adjacent faces are touching each other. Let's get back to this coordination number. coordination number is number of atoms surrounding an atom. So let me select one particular atom here. Okay, I have a red atom which is at the center of this particular phase. So you can see that it is clearly surrounded by what is this? Four atoms which are at the corners of that particular phase. Which they are at a distance. All are of equidistant from this, at a distance of maybe a root 2 by 2. This distance we just calculated distance between these two. This is a root 2 by 2, or let's say phase diagonal by 2. Okay, so are there the only atoms which are surrounding it? No, we have 4 more here, and we just now seen that this black sphere and this red sphere are going to touch each other. So we have to count these 4 also as the atoms which are surrounding it. So is it do you have any more atoms? Let's see. Let me extend this particular unit cell. So adjacent to this, I have one more unit cell here, and it has also 4 atoms at the centers of these faces. So total there are going to be 4 plus 4 plus 4. There are going to be 12 atoms that are going to surround this particular red one, and so coordination number is 12. So this is little difficult to understand. What I advise you is look at your room and look at you treat it as a cube, and take a face and take a atom at the center of the face, and see what are the atoms that are nearest to it. So, and don't forget that distance between this particular atom and this particular atom is same as distance between this particular one, So in fact this is touching this, and this is also touching this. So this length is 2r, this length is also 2r. So that makes coordination number as 12. Density. So density of crystal is same as density of this particular unit cell. Density is mass by volume. Volume is a cube, and mass of the unit cell is equal to mass of each atom into number of atoms present in a unit cell. N is effective number of atoms, and mass of each atom you can easily find it, gram atomic weight by Avogadro number. So that makes D is equal to again N into M by V into N. So what is N, small n here? So we have seen that effective number of atoms is 8 into 1 by 8 and 6 at the centers of the sorry about this, I have a problem here. This is 6 into 1 by 2. This is not 1 by 6. This is 6 into 1 by 2. That means you have effective number of atoms as 4, because one sphere which is at the center of the face will contribute is half inside this unit cell and half in the adjacent unit cell. So that way this should be 6 into 1 by 2. Effective number of atoms is 4. Substitute that value. This is the gram atomic weight of the atom, and this is Avogadro number. This is the volume, that is a cube. There is packing fraction. Packing fraction is the fraction of total volume occupied by the atoms. This packing efficiency, how much is filled, how much is vacant, how much is void, this we'll talk about here. Again, you have packing fraction is 4 into 4 by 3 pi r cube. The reason for this is there are going to be 4 atoms. Effective number of atoms in a unit cell is 4. 8 into 1 by 8 plus 6 into 1 by 2. 6 into 1 by 2. So that will make it 4. Effective number of atoms is 4. And volume of each atom is, we take it as a sphere, it has a radius r, it has volume 4 by 3 pi r cube, and a cube is the total volume of the cell. So rest of it is a void. And what is the relation here between a and r? We consider the phase diagonal. Phase diagonal we had 4r is equal to root 2a. That value is 0.74. And remember this has been highest till now, whatever we learned. In fact, this is the highest and best packing that is possible. We know that 100% is not possible because we are trying to fill a 3D space using spheres, not cubes, using spheres. So they are not really going to be effective. They are not going to fill it 100%. So only 75% is filled, and whatever the efficiency we have got in this particular FCC is the best that is possible. We'll see why it is best. We'll see what are the why you can't have more than 74%. That makes this void fraction as 0.26. Okay, right. So hexagonal unit cell. This is the fourth one we are learning. What is this hexagonal shape? Right. You take a regular hexagon and extend into third dimension also, so you get an hexagonal unit cell. Let's take up one first layer. That is, you have these 6 spheres here. Sorry, 6 plus 1 at the center. So total 7 spheres that are that will form a regular hexagon. So over it, I'll try to build one more layer. So that will that is these 3 spheres. So look at here where I am placing this particular atom. That is in between 3 atoms. I have some kind of depression here. So this is able to rest on it. Not only it able to rest on it, and it is also touching the another sphere which is in the another adjacent depression. So this is the second layer, and third layer we have something like this. So this is the hexagonal unit cell. Let's see how many atoms are present in this. So before that, let's have another look at this hexagonal unit cell. There are going to be 7 plus 3 plus 7, 14 plus 3, 17 atoms make a unit cell. There are going to be 17 atoms. This is how they are present. These 3 atoms are at the depressions. They are at depression 1, 2, 3. They are at the depressions of this particular first layer. So we have 7 plus 3 plus 7, 17 atoms to make a model. Okay. If A is the side, H is the height of a diagonal. This is the height, this is the side. This is side, this is also a side. Like this, no, this is this and this are equivalent sides. So you have A is equal to 2R. You have seen that this is the line joining the 2 adjacent atoms which are touching each other. So A has to be equal to 2R. And H is, I'm directly writing here, H is equal to 2A into square root of 2 by 3. This using geometry you got to get it. I'm not doing it here. Maybe at later part I'll explain you why this height is equal to 2A into square root of 2 by 3. Okay. So fine, let's for a minute I'll go ahead with this slide. Okay, hexagonal unit cell. Each unit cell owns how many atoms? Let's see. I have there are 6 at the corners of this particular face, and 6 you have. So total 12, and contribution towards this is only 1 6. Why only 1 6? This corner is common to 6 such unit cells. So this is one. This angle is 120, right? This angle is 120. So you can have 2 more because it's 360 minus 120. So you can have 2 more unit cells here in this plane and 2 in the above plane. So total there are 6 unit cells which have the same corner as this atom. So an atom which is at this position can contribute only 1/6 to this particular unit cell. So there are 12 such atoms, 6 in this first layer, 6 in the last layer, that is 12 into 1 by 6. Now let me go to this particular sphere which is at the center of the face. So there are 2 such spheres which are at the centers of the faces. and you know that this phase, this polar phase, is a common phase for two unit cell, one this and one above it. So this phase is common, and even this atom is common for uh, these two unit cells. So this is this contribution of this atom towards this particular unit cell is 1 by 2. There are two such spheres, one here, another here. So 2 into 1 by 2. This is already equal into 1 by 6. So that's it. You have 3 more here. So there are 3 more. They are completely inside it. They are completely inside the unit cell. So the contribution has to be 1. So 3 into 1. That will make it effective number of atoms as 6. So if you take a unit cell, there are going to be 6 atoms. Coordination number. Coordination number is the number of atoms surrounding a particular atom. So you have to select one particular atom here. I'll take this black sphere which is at the center of a face of this hexagonal. So this is surrounded by 6 red spheres which are at the corners of this particular face. So 6 are there in this face. What about these 3? Are they touching it? You remember that these 3 were put on the depressions are formed by here. So this is there in the depression formed by 1, 2, 3. So this is just below the depression formed by 1, 2, 3. These 3 atoms. So definitely this sphere has to touch this one. So this one is not only touching these 6 red spheres. This is also touching these 3 blue spheres. So similarly you will have 3 more blue spheres, blue atoms above this unit cell. So that will make coordination number 12 for hexagonal unit cell. Okay, this is about coordination number. Density is mass by volume. Again, mass is equal to mass of each atom multiplied by the number of atoms that are present. Then you get again D is equal to Nm by V into N. This N is the number of atoms that particular unit cell own, effective number of atoms, and we just now calculated that it's going to be 6. So N is 6 here, that is 12 into 1 by 6, 2 into 1 by 2, 3 into 1. So 12 at the corners of the faces, and 2 at the centers of the face, and 3 completely inside. So that is so what about volume here? Let's look at volume. Volume of this this kind of thing is like volume of the base into height. So volume of the hexagon is base area into height. So this is the base. I'm looking from the top. This is the top view of this hexagon. So what I do is I'll have a triangle here. I'll join this ends of a side with the center of the hexagon. So that will give me a equilateral triangle. So volume of this is equal to 6 into this root 3 by 4 into a square. This particular one is the area of one particular equilateral triangle. So we have 6 more equilateral triangles here. There are 6 more equilateral triangles. So that's why 6 into this whole thing is the base area of this particular structure. So this is the base area, and that into height. We just now said height is 2a into square root of 2 by 3. So packing fraction, packing efficiency, how much is filled, how much is vacant. So packing fraction is volume of the atoms in a cell by volume of the cell. So again, packing fraction here is equal to 6 into what is this 6? This is our small n, effective number of atoms in a particular unit cell. So it owns 6 atoms. Each atom has a volume of 4 by 3 pi r cube. So I have to get a relation between R and V. So A is equal to 2R. That is the relation, but that's not everything. And you have to have. Just now we had a relation between A and V. I'll write it again. Now what is the packing fraction? Packing fraction is 0.74. And if you remember that, packing fraction here is also 0.74 and is also the same value for FCC also. So, and we learned that that's the best packing that is possible. 0.74 is best packing that is possible. Can't have efficiency more than 74%. So that makes void fraction is 0.26. Let's get back to this. We just now said that this volume is equal to 6 times this area of this equilateral triangle with multiplied with height of the hexagon. So this is the volume, and again I know the relation between A and R, so I substitute this value, I get this value, this numerical value. So this is one thing you might have noticed by now. Lot of things are similar for hexagonal unit cell and FCC. What was the coordination number in FCC? And that was 12, and coordination number for hexagonal unit cell is also 12. Packing fraction is 0.74 for both of them. So there are some similarities. Why there is this similarity existing between these two, and also why this 74% is the best efficiency we can ever have using spheres of same radius. Again, you have to remember this. This we are taking the spheres of same radius. So why 74% is best efficiency? We'll all discuss all these things at a later stage, and let's talk about this packing fraction. Close packing. This is close packing. So let's say I have tennis spheres, tennis balls, where I got to fill a 3-dimensional space. So I have a tennis ball here. This I want to put it on the fill it whole of your room. There is a room, right? You're sitting in a room, so I want to fill that particular room with as many tennis spheres as possible. So maybe I'll have a first ball, first sphere, something like this, and I have a first row, something like this. So I want to have another row adjacent to it. And remember this, I am worried about this packing. I have to have closest packing. So this time I have to have another row which is not exactly below it, a little shifted to right, because if it is exactly below it, they are not really close to each other. So if I put similarly place all these yellow spheres on a particular floor, this is how it looks. I can't put more spheres than what I have here now, in any other arrangement. Now this is about first layer. I want to have one more layer out. I am trying to fill another layer over it. Again, what I am doing here is I am taking some spheres of same radius and trying to fill a 3-dimensional space. So already filled one layer, now I want to fill another layer, so I put one more sphere. If you look at carefully, I have placed a sphere exactly above the first one. Sorry, this is not really stable. Not only this is stable, this is not a best efficient packing. So maybe I have to place this sphere in the depressions that are caused by 3 spheres in the layer 1. So this is not this is ruled out. So this is the best way of packing it. So minimizing the voids, minimizing the empty space. So if I continue placing the spheres like this, I have a second layer above this first layer. So again I repeat, here I am trying to place spheres in a particular three-dimensional space to such a way that I minimize the whatever, I minimize the empty space, void. I minimize the void, and I want to increase this packing efficiency more. I want to have this packing efficiency more. Okay, so this is a kind of void. So even though I tried my best to fill this three-dimensional space efficiently, still I have some voids because I am filling with spheres. So we got to have some voids, some empty spaces in this. You can clearly see that there is going to be some empty space here. Similarly, you have one more empty space here. This is empty space, and there is a difference between these two. This and this and this. These are formed by four spheres. 1, 2, 3, and the fourth one. Right? And this is not formed by four spheres. I will discuss what it is formed of. But you can see that this is a see-through void. You can clearly see through that side of the arrangement. So here, sorry, this is blocked. So this is blocked. So there are both different kinds of voids. So this void is called void is an empty space. What is a void? Void is an empty space. This is a tetrahedral void. This is called tetrahedral void. This is because of four atoms here. Okay. So, and this is called octahedral void. This is called octahedral void. I'll discuss more about this in the next slide. Tetrahedral void. Look at this triangle. This is at the center of this triangle you have a void. This is tetrahedral void. This is formed by four atoms. 1, 2, 3, 4. 3, 4. So there are four atoms. Let me pick it outside and okay, this is four atoms. So these are the four atoms. You have got a void in between these four. This is tetrahedral void. This is tetrahedral void. Okay. And what about this? I do have a void here. This is a kind of yellow colored one. So yes, you have a void here. This is also formed by again four spheres. This one sphere, one, and one. So four spheres. So this is that particular void. This is tetrahedral void. Can you imagine there is a empty space in between these four atoms? This is tetrahedral void. This is tetrahedral void. Okay, so these are all tetrahedral voids. You can see that this is tetrahedral void. This is tetrahedral. This is tetrahedral. These are all tetrahedral. Tetrahedral void is formed by four spheres. Four spheres of same radius. Okay. What about octahedral void then? Okay, octahedral void. Let's see this octahedral void. Okay, so you look at this particular void. This is a see-through void. I call it a see-through void because there is no obstruction. Like you can just see through the other side. So this I want to collect. So this void is formed because of six spheres. You can see that six spheres. There are three spheres and again three more in a reverse way. So this is I'm trying to pick it out so that you can clearly see that. So there are how many atoms? There are six atoms. They are forming, and look at here. Centers of this yellow spheres is in a different plane from the centers of this red spheres. So this is one above the other. This one layer above the other layer. So this is tetrahedral void. This is tetrahedral void. I have a layer 1, layer A, layer B. No, I wanted to fill this three-dimensional space. I filled only two layers. I want to fill some more layers. So I want to have a third layer. So I want to place this sphere. So definitely again I have to place it in one of the depressions. So this is one depression, this is another depression, this is another depression. So I can place it over the depressions formed by the second layer now. Yes, this is one possibility, and this is another possibility that you can put it over here. What is the difference between these two? If you carefully observe that, this is exactly above an atom which is in the layer A. Right? This is like look at here. So that is going to come exactly over this particular atom. So this is again of layer type layer A. So this one is not exactly over any atom which is in the layer A. You can clearly see that it's blocking the see-through void. This is over a see-through void. So this is not above any atom. This is only above this octahedral void. So if I try to complete fill this particular third layer with this kind of arrangement or this kind of arrangement, if you carefully observe it, I can't have both. I can't be placing the spheres above octahedral void. And where is this thing? This is in if you carefully observe it, this is you are placing here. This is a tetrahedral void. This is a tetrahedral void. So I am placing a sphere over the tetrahedral void. So this sphere has nothing to do with the tetrahedral void, because tetrahedral void is deep inside this 3D space. So over it I am trying to put one more sphere there. So this sphere is over octahedral void. Okay, and what you might observe is, if I place one sphere over here, next sphere comes here, and which will this will not allow this another sphere to come here. So that is a problem. So that means if you are placing an atom over a tetrahedral void, you can't place an atom over octahedral void. So third layer is either A type, that is, you can have these yellow spheres which are over tetrahedral voids, or C type, that is entirely a different one, neither A nor B. These atoms are not above any atoms. So it can, third layer can be either A, you have an option here, it can be either A or C. Okay, let's see what happens if third layer is A. So again, you have similar to A, you have as a third layer. So I place one above the atom which is in the third layer, first layer A. So I go on filling this layer A again. So you have layer A. So this is off. Then we have AB pattern, type of pattern we have on. So AB type of pattern. If instead of choosing depression over tetrahedral, if we choose a depression over octahedral, then let's see what happens. So we have a layer C, so third layer. So look at carefully, I am putting over a octahedral void. So these are all octahedral voids. So I can place all the overall octahedral voids. So this is third layer, and this is layer C. Okay, so we have ABC. Why this is C and why it was A earlier case? Because it's exactly above it. That's why it's no different from earlier. It was third layer was no different from layer A. This time this layer is different from layer A. So you have ABC type of closed packing arrangement you have. So what is this AB and what is this ABC? Let's get back to this AB pattern. Look at this lines joining the centers of adjacent one. So you have AB type. This is how AB type. This is It has hexagonal shape. It's not easy to understand. Look at here. There are one atom. This is surrounded by six atoms. This is A. And if you go to the next layer, you have 1, 2, 3. You have 1, 2, 3. These are the second layer atoms in hexagonal unit cell, if you remember properly. Again, the first layer, again I get back to layer A. So that is, again you have 1 here and 6 surrounding it. So it is called hexagonal closest packing. This is called hexagonal closest packing. This is HCP, hexagonal closest packing. ABC type. If AB is hexagonal closed packing, then what about ABC type? This is look at here. We have ABC. So this is A, which is again B, which is different from A. Again we have C, which is different from both A and B. Now again A is coming here. So if I have a structure like this, so it looks like it has a cubic shape. Can you imagine that? It has a cubic shape. It's not going to be easy. So it's right now try to understand that ABC is a cubic shape. In fact, it's an FCC, closest packing, cubic closest packing, and this is an FCC. ABC type is pattern is FCC, and AB is HCP, hexagonal closed packing. ABC is cubic arrangement. AB is hexagonal arrangement.